In the model that we have developed so far, based on circuit elements, we now can describe quite a bit about how a battery cell works. We have an open circuit voltage that is a function of state of charge. We have an equivalent series resistance, and we have a model of diffusion voltages that uses resistor and capacitor components connected in parallel. This models probably the majority of the dynamics that we see in a lithium-ion battery cell. But there are some things that it is missing that become important if we have a very high requirement of accuracy in some kind of an application, such as estimating state of charge in a hybrid electric battery system. One thing we notice in a real battery cell is that if the cell has been active for a while and then it is allowed to rest for a long enough time, the diffusion voltages in the prior model will decay to zero, because in the resistor capacitor network, themselves connected in parallel, any capacitor voltage is going to self-discharge through its resistor. And then because the cell is at rest, the current through the R0 is zero, and so eventually the voltage in the cell model that we've developed to date is going to converge to the open circuit voltage of the cell. But when we attempt doing this with a real cell, we have active current going into the cell or out of the cell for a period of time, and then we allow the cell to rest, we notice a different behavior. The voltage of the cell does not decay to the open circuit voltage and converge to that. It decays to something else. We find that for every state of charge, there's a range of possible stable voltage values, not really open circuit voltage values, but they are equilibrium values that can be maintained for many days. We've done lab tests and we know that these voltages don't just have a slow decay rate, they have a zero decay rate. This picture on the right is an attempt to illustrate this, and it's not a perfect tool for doing that, but maybe it will at least convey part of the message. What this picture shows is a cell in a lab test. This is actual lab test data where we have started the test with the cell fully charged, in this case to 3.6 volts. And we have slowly discharged this cell along this line down to 2.5 volts, which corresponds to the 0% state of charge point. And when I say slow, this is a C/30 rate, meaning that one step of this picture took 30 hours in order to accomplish. Then we slowly charge from 0% up to 95%, and then discharge from 95 down to 5, and so forth, and we get this resulting voltage plot with all of these inner loops in it. Because the cell current is so low, a C/30 rate is very, very low, and we think about what is happening in this model, the IR drop is just about zero. It's not zero, but it's very close to zero. And the drop across that element is also very close to zero. And so I would expect this lab test to give me essentially open circuit voltage plus or minus a very small amount. And it does give me open circuit voltage plus or minus something. That plus or minus something is a much larger amount than we would expect from the circuit diagram that we've seen so far. And furthermore, if I were to stop this test and actually rest and apply zero current, the voltage that we see in the plot does not really change appreciably. It does a little bit, but not appreciably, whereas in the circuit description we have so far, we would expect the voltage to converge to OCV after a short period of time. So what this means is that the the voltage of the cell, the rest voltage of this cell, is not equal to open circuit voltage. The rest voltage of the cell, in fact, depends on the history of how this cell was used. So if I have recently been discharging, the rest voltage is going to be lower than if I had recently been charging and I'm encounter the same state of charge, maybe 60% or something. Whenever we see this kind of phenomena, that's evidence that there's hysteresis in the behavior of whatever we are modeling, in this case a battery cell. Hysteresis comes from the Greek. It means to arrive late, and it means here that the voltage behavior lags behind what we would think it would be. It doesn't arrive to the voltage we think it's going to arrive to as quickly, because there's this component in it where the voltage is getting stuck. If I'm discharging if I have recently been discharging, the voltage is stuck lower than I would expect. If I have recently been charging, the voltage is stuck higher than I would expect. So there's a big distinction between hysteresis and diffusion voltages, in that if I allow the cell to rest, the hysteresis voltage does not change. It remains constant. Whereas if I allow a diffusion voltage, if I'm talking about diffusion voltage and I allow the cell to rest, that diffusion voltage will decay to zero after a period of time. So a diffusion voltage is a function of time, whereas a hysteresis voltage is in some sense a function of SOC, and in particular it's a function of how the state of charge has been changing recently. This hysteresis is not well understood. You will see in later chapters when we talk about the physics of how a battery cell operates, we don't actually describe hysteresis in those chapters. It's not well understood, and in fact, it is thought that this phenomena may occur for different reasons in different lithium-ion cell chemistries. So chemistries that are, say, iron phosphate based and use an olivine one-dimensional electrode material may have hysteresis for a different reason from why another material would have hysteresis, and so that complicates the physics modeling. And at this point, I'm not aware of any really good physics-based explanations of hysteresis. And as I said, for some applications it's important. So let's just suppose my principal objective of making a battery model is to put it in an algorithm or a computer code that makes measurements of current and voltage and tries to use those to estimate the state of charge of a battery cell. And estimating state of charge is easiest when the cell is resting, because all of the other dynamic effects are gone. They decay to zero. But suppose in this cell test that's shown here, I measure a voltage of 3.3 volts. And I'll try to draw that line. You can see that 3.3 volts could correspond to a state of charge as low as 10% and as high maybe as 95%. And if I don't understand the hysteresis component of voltage and I just try to look up a state of charge in a voltage curve like this, I'm going to have a huge margin of error, anywhere between 10 and 95%. Well, that's an 85% window, and that's useless for any application at all. So hysteresis is important to know if I want a really precise estimate of state of charge and some other things also. I wish I could present to you a fantastic model of hysteresis that really matched lab test data very well. I cannot do that because I do not know a model of hysteresis that matches lab test data really well. I did have a master's student some years ago come up with a model of hysteresis that was quite good, but it was very complicated. It was much more complicated than anything else you will see in this course in terms of computational complexity anyway. So while it was an accurate model, it wasn't a very helpful model. what I will present to you here is a reasonably simple model of hysteresis that is fairly close to observations that we see in the laboratory, but there's still a lot of room for improvement. So it's my hope that in the literature over the next few years we will see some researchers with a better understanding of material science and physics who will come up with some kind of a lower level understanding of this hysteresis to even explain why it exists. At this point in time, we're not entirely sure why the hysteresis exists. We just know that it does. And if we know why it exists and have a good physics-based model, then there's a really good chance that we could create a phenomenological circuit type of model as well that could explain the hysteresis. So what I will present here, I just wanted you to know this is an okay model of hysteresis. It's better than no model at all, but there's a lot of room for improvement. We will define H of Z and T to be the hysteresis voltage as a function of state of charge, that's Z, and time, that's T. And the time derivative of state of charge is dz by dt, which we denote by z dot. If with this nomenclature, then we define a model of hysteresis with this differential equation, which says that hysteresis voltage changes as state of charge changes. Remember, this is a function of the history of state of charge, not of time directly. So H changes as Z changes according to this assumed form. And it's a first order differential equation. And it says if there's a maximum hysteresis, capital M, at this state of charge and this rate of change of state of charge, and there's a present value of my hysteresis state in this model, then if that difference between the present hysteresis and the maximum amount is large, then basically my rate of change of hysteresis is large. The farther I am away from this target M, the faster I will move toward that target. And the closer I am to that target M, the slower I will move toward that target. Gamma here is a constant that is a rate constant, which tunes how quickly or how slowly the overall process works, not with respect to time, but with respect to rate of change of z. And the sign of z dot simply makes this equation stable, so dH by dz is always, so the H is always moving towards M, whether I'm charging or discharging is the idea. So if I'm far away, it wants to converge quickly. If I'm close, it doesn't want to converge quite as quickly. And overall, the shape of this curve, if I plot as a function of state of charge, is exponential. So the hysteresis state exponentially converges toward the maximum amount at that state of charge. And if we look at what's happening in this picture, we see that that's at least sort of true, that when I change the direction of current, it very quickly moves toward the other side, the other boundary of the loop, and then as I get closer, it slows down and more slowly approaches it. So it's not quite exponential, but maybe exponential isn't too bad a guess for what that shape looks like. We choose this M, this maximum hysteresis value, to be positive when we're charging, so Z dot is bigger than 0, and negative when we're discharging. Notice that this figure here, by the way, is not M. This figure is really, at least the outside of this figure. You could say that the overall envelope function, which I'm trying to indicate there, is going to be OCV plus M. So if I subtract out the open circuit voltage of this cell from that, my M in this example would be some envelope that would look like this, versus state of charge. So it closes at 0% and 100%, and then it is roughly some constant in between. So this would be plus magnitude of m, and this is minus magnitude of m down there. That's the idea. That's the only rationale behind this functional form, is that our observation indicates that an exponential shape is at least close to what we observe, and this equation gives us that exponential shape. So again, in the equation, m minus h says that the rate of change of hysteresis voltage is proportional to the distance away from this major loop, and that gives us a kind of an exponential decay. Gamma says how quickly, relative to a change in state of charge, the hysteresis converges, and sine of z dot forces the equation to be stable. In our model equations so far, we have had some differential equations. We had the z dot equation equals minus I over q. That's the derivative of z with respect to time. And we've had the dir1 by dt equation, which is also a derivative with respect to time. But our hysteresis equation so far is not. It's a differential equation derivative of h with respect to z. And in order to fit hysteresis into our model, we have to manipulate the equation to be a differential equation in time to match in concept the equations we already have. And we perform a mathematical trick using the product rule, or chain rule, I guess, of derivatives. So I have dh by dz, and I know that's equal to this, and I multiply both sides of the equation by dz by dt, and when I do that, this dz cancels that dz, and the left-hand side becomes dh by dt, or h dot. The right-hand side, so the left-hand side, I do that in symbols to get h dot. The right-hand side, I actually insert what I know dz dt to be. We know that it's equals, z dot is minus I over q, possibly with this Coulombic efficiency, eta of t factor. So I will, for generality, I will keep the eta factor here. And also, if I have x times sine of x for whatever x is, any arbitrary thing, that's equal to the absolute value of that arbitrary thing x. So z dot sine z dot is just the absolute value of z dot. And so here I've got z dot and I've got sine z dot, and that gives me together the absolute value of z dot, and the absolute value of z dot is the absolute value of that thing right there. So multiplying out, I have gamma times this, the minus eta I over q, multiplying m and also multiplying negative h. And that's what we have down here in this equation. There is our differential equation in time, continuous time equation, modeling this hysteresis effect. And we can convert this to a discrete time differential equation using the method we saw in the previous section, where, this looks like h dot equals a times h plus b times an input, which is m, and that's my continuous time a and b. And I can get a discrete time version out of that. By e to the at would be my discrete time constant out front, and that integral that we had before, or 1 minus e to the at, I guess, would be the other term. And that's what we did here. So compare this equation to this equation using the method developed in the previous section, and you will see, this negative absolute value of eta I gamma over q becomes e to the minus absolute value of eta I gamma delta t over q, and so forth. That's one of the reasons I developed in a general way the conversion from continuous to discrete, so that it would be a fairly straightforward step to apply here rather than having to again perform all those operations on this example. So that gives us our discrete time hysteresis equations, and something that would have to be modeled in this would be what is m. And the simplest thing to do would be to say capital M is some negative constant m times sine of current, which would mean, going back here, it looked like from our lab test that I have a elongated oval shape of hysteresis curve, but some parts of the lab test make it a little bit less certain what's happening around here, so I don't want to trust the oval too much there, it turns out. And so if I replace my hysteresis model with simply a plus m when I'm charging and a minus m when I'm discharging, where m now is a constant, then that's a fairly decent estimate of the outer loop of hysteresis. And to get plus m when I'm charging, I have to multiply the sine of current by minus 1, and the same idea when I'm discharging. So that is the motivation for saying perhaps this is an okay outer loop. There's some evidence that the outer loop changes depending on the magnitude of current, and that is not captured by this model, so that's a limitation. But this is the model I end up using for this dynamic hysteresis. And in this representation, we can show that the hysteresis state, h of k, is always captured between plus and minus m, and h of k has units of volts, by the way. When we're attempting to find the model parameter values, in this case we want to find the gamma value, but there's also a necessity to find eta and q and the resistor values and capacitor values. Whenever we want to find the model parameter values for the final model, it actually turns out to be a little bit easier to do mathematically if we use an equivalent representation, but a somewhat reorganized representation. And in this new representation, we scale the hysteresis state to be between plus and minus 1. And the only difference you see in the H equation is there's no M here. Gone. And so H is a unitless value between plus minus 1. And when I want to convert H into a voltage, I have to multiply by M, where M then has units of volts. Okay, we're going to see that in the next section. So then I have what we call a state equation for hysteresis and an output equation for hysteresis that will become part of the model. You could look at that figure of our lab test result, and coming back to it here, I'm going to see if I can zoom in a little bit more so we can see some of the detail in the figure. The reason for using the exponential shape, as you can see, there is curvature here. There's curvature. The hysteresis bends as you change state of charge. And it sure does look like hysteresis changes quickly when I change the direction of current, but then it slows down. You could also argue that there may be some instantaneous change in voltage that's right away. As soon as I change the direction of current from the previous direction, there's an instant change in hysteresis, and then after that there's a kind of a dynamic change that is exponential. And I have found sometimes that the model can be made better by including another hysteresis term, which I call instantaneous hysteresis. And here we define a variable S to be the sign of input current. And if the input current is not zero, if its absolute value is bigger than zero, or if the input current itself is not zero, then Sk, the sign of current, is simply the sign of I of k. If I of k is positive, Sk is 1. If I of k is negative, Sk is minus 1. If I of k is 0, this equation says, I don't know what to do, so I go to the otherwise case. It says, otherwise, I reuse the previous value of Sk. So Sk is the sign of current, but it has memory that remembers what the previous sign of current was if I was resting. If I am resting now, it remembers if I had previously been charging or discharging. So with this basically instantaneous model of the sign of current, my instantaneous hysteresis voltage is M0 times Sk, and then the overall hysteresis voltage is this instantaneous component M0 Sk plus M times Hk. Not all models of not all cells will have hysteresis. Some models will have only the instantaneous part, some models will have only the dynamic part, and some models will have both. It depends on what you find works best in practice to capture how your cell works, and also how much complexity you are allowing yourself in the application of your overall model.